Hello again. Today we will be learning about derivatives, primarily derivative equations, as in first derivatives, second derivatives, and the such, through the lens of physics. So while this is a math lesson, there will be some physics involved. However, it will be very rudimentary. Now, let us begin. Let us imagine that there is a car. This car is moving, and it starts with a speed of 0. Now, for simplicity's sake, we will consider that the jerk of this car is also 0. That is, its acceleration is constant. So, we have the change in acceleration, or yes, we can start in such a way. dA being the partial change in acceleration over dt, essentially being the instantaneous change in acceleration, is equal to 0. Now if we integrate this, we get dA dt is equal to c being some constant. Oh, I apologize, rather. dA dt. Oh, once again, I made the same mistake. Now, A is equal to C, some constant C. Now, this is simply because there is no instantaneous change ever, hence it being 0. So the acceleration is some constant. Now, let us imagine that this acceleration, therefore, forms on the graph we have here such a function, wherein this would be c, and this would be the acceleration with consideration of time. Now that we have that, we could say that when we integrate this, meaning that essentially acceleration can be written as dv over dt, the instantaneous change in speed. Now, is equal to c. Now, if we were to integrate this, that is, take the sum of all the instantaneous accelerations to get the speed at any time, well, we would be looking at the area under this curve, under the curve here. Why is that? Well, because at this time, you have such and such acceleration. At this time, you have such and such. And you keep adding those up at very small lengths of time, and you get essentially the acceleration over a period, the sum of the accelerations over a period, and hence the speed. So essentially, it's the area under this, with essentially this being a rectangle, wherein the height will be simply c, and the width will be t. And as you can see, this when we look at this equation, and we take the derivative as we normally would with a polynomial, you would get that v is equal to cx plus q, some constant q. And indeed, it is the same matter, wherein we can take the change in speed by taking the area underneath the rectangle. It's represented by c, oh, I have put x, but it's rather ct. I should show this in more detail beforehand. Essentially, you have dv is equal to c dt. Once we take the derivative, it's v is equal to ct plus q, some constant q. Now, as I said before, we have the rectangle c times t, that's the area under the rectangle. But we ought to consider that that's only the change, or rather the sum of the changes. If initially the speed was not 0, that is, q was not equal to 0, or rather if the speed was not equal to 0, we would have some non-zero q value being equal to the initial speed at time of 0. Now that we have this, we encroach upon distance. Or rather, displacement. So we therefore have, with speed being equal to the change in displacement per unit time, displacement in this case being ds. Now, if we once again draw a graph for the v is equal to ct plus q equation, we arrive at a linear relationship as follows. Assuming q is some positive value. If it was not, then the intercept with the y-axis would be below the origin. However, we will do so. Now, consider that in much the similar way as to how the instantaneous sums are equal to the change, in this case also, the instantaneous sums being the area enclosed by the function and the graph, as follows, are the distance traveled at that time. And indeed, yes. So, when we do this, there are two ways to do this. The first one is obviously taking the integral, as we are typically used to. This would be as follows. Q dt. And once we integrate both sides, we get s is equal to ct squared over 2 plus qt plus some initial displacement d. Now then, although we have this equation, we may once again look to the graph. This would be q, this point here. And this point here would be, or say we wish to find that time t. This point here would be q plus ct. Now, this is, if you turn it, or even if you imagine a bit, the function outlined here is a trapezoid. Or rather, a rhombus, perhaps. Sorry, I don't know the name of shapes. Trapezoid. Indeed, I believe it to be the case. It is a right trapezoid. Now, consider that this is one base and this is another base. So, we do the area of a trapezoid. And this is the height. So, we do the height times q plus qt plus ct. I apologize, not qt. Just q it should be. Plus ct. All over 2, being the average of the two bases. And in turn, this becomes equal to qt plus ct squared over 2, which if you look again, is the same as this, that we'd gotten in the displacement equation. And indeed, we can say these to be equivalent, except for the d here. However, that is only added because we are, with the area, only measuring the change, not the initial value, and the d would be the initial value. Now, regarding this matter, this is a one can regard that velocity is the first derivative of displacement, and acceleration is the second derivative of displacement. And respectively, acceleration is the first derivative of velocity. We could further add jerk, which would be the change in acceleration. However, there is no need for this, and it will only serve to make it more complicated. However, it ought to be mentioned that we will indeed get a third power polynomial. Now, let us try with an example, as follows. Our initial acceleration, or rather, since it is constant, our acceleration is equal to 3 meters per second. Our initial position, or rather, let us say our initial velocity is equal to -6. And our initial position is equal to, our initial position is equal to -2. Now, if you pay attention, the -2 rather, would be equivalent to the d beforehand, and likewise, with velocity, the -6 would be equal to q. Now, we could have v at 1 or v at any other value. However, this simplifies it. Now, once again, taking the derivative, dv dt is equal to 3. We have dv is equal to 3 dt. We integrate it as follows. Or rather, let us go with v1, I believe. 3t plus c. Now, we have v1 is equal to 3. Is equal to, I apologize, 3 plus c. And yet, we also have -6 is equal to v1. Thereby, we may conclude that c is equal to -9. And indeed, it is as such, in order to fill our initial requirements. Now, furthermore, we must find the displacement. And by the way, this example only serves to demonstrate. Although it should cover most grade level requirements. Now, we have v is equal to 3t minus 9. This is our initial condition equation, whereas this equation that I outlined is the general solution. Those terms are distinct. The general solution is for all cases, yet the initial condition is for when you're given some sort of condition that will tell you the constant value in some way or another. Now, we further have ds dt is equal to 3t minus 9. Of course, ds dt being the velocity. And once again, we multiply both sides by dt. And integrate as follows. Plus, let us call this d. Oh, and regarding my usage of c, this c used here should really be equated to the following q. However, I am more so used to using c. It is far more standard when integrating. Now that we have this, we must once again return to our initial condition, wherein S2 is equal to 3t squared over 2, 9t, plus d. And once again, as you can see, S2 is equal to -2. So on this side we have -2, and on this side we have 2. Oh, I should have placed 2 squared here. 2, not t. And consequently, we have, I believe that would be 6 minus 18 plus d, if I am not mistaken. And this in turn yields 10 is equal to d. And by the way, once again, this is our general solution here. And we simply replace the d with 10, and thereby arrive at our, I suppose, final solution. Yes. Although, yes, I believe that to be correct. And yet, we may further explore integration, more so specifically other formats of problems or other archetypes of problems In the next video, part 2 of this video, I should mention that this is a 2-part video, as it is a bit longer than usual. And the next video will consist of exponential integration and exponential derivative equations. I hope to see you next time. And once again, we will return to physics, specifically Newton's law of cooling. I hope you've enjoyed this. Thank you very much.